Hello, welcome to Emergency R, where the goal is to get you going with your data as fast as possible. As a reminder, all of these videos, if you go in the description, there's a table of contents so you can skip to the part that is most relevant to what you want to do. And if you want to follow along directly with this video, the CSV file that I'm using is available from a GitHub site that is linked in the description. So today I'm going to go over some quick statistics that you can do in R. So this is not a video about statistics. This assumes that you already have a little bit of knowledge and just you want to know how can you do this stuff in R. So I'm going to make a new file, a new script for my what I'm doing today, and I'm going to copy in this code for reading in my CSV file. Okay. And so I'm putting my cursor up on top and hitting Control Enter to run this line. And then this str line is just going to give me a preview of what is in this file. So I can see these various columns that I have, what type of data they have, a little bit of a preview of what's in there. So this is some agricultural data about some plants, and what I'm most interested in is the yield of the plants. So like, how much am I getting back at the end of the day that would be of commercial value to a farmer? So I examined that data before looking at it with a histogram just to make sure it was distributed okay. Right, I use this $sign to extract a particular column that I want to look at, and the hist function makes a histogram. So I hit Control Enter to run it, and I see that it's very skewed. So we have a few extremely high values and most of them are small. So what I did before was log transform that to get something that was more normally distributed. So for all of my statistics, I probably want to keep working with the log transform data, especially once I'm going to start doing things like linear regression. So I probably just want to make a variable that already is log transformed, so I don't have to transform it every time. So I'm going to make a new variable here, and I can add it right to the same data frame. And so what I'm going to do is I'm going to type a $sign again, like I was trying to get to one column. And I'm going to type a new column name that doesn't already exist yet, that I want to create. And then I'm going to use a less than sign, followed by a minus sign. This is an arrow, which is the assignment operator in R, so that's saying I want to put some value into this variable. And what I'm going to do is I'm going to copy and paste my log transformation of that column. So once I run that, if I look at the structure of my data again, now I can see I have that column added to the data frame. And I could do a histogram just of that column. Now let's explore some statistics that we can get on a single variable. So if I look up mean, right, I get this mean function, and there are a lot of related ones that have similar arguments. So if I want to get the mean of my transformed yield value, or my transformed yield variable, do mean parentheses, and again I'm going to make my life easy and copy and paste this whole variable name in there. And if I run that, I actually get NA, which means missing data. And obviously I have data here, so what happened? Well, by default, if there's any missing data at all, it returns missing data. If I'd rather just have the mean of whatever is there, which, let's face it, 95% of the time that's what I want, I type na.rm, all lowercase, then an equals sign. I'm putting spaces to make it easier to read. The spaces are optional. And then in all caps, true. So if I do that, then I get the mean of that transformed data. Likewise, I can get the median. That also has an na.rm argument. I could get the minimum. These all of these that I'm showing right now will give NA if you don't put NA.rm equals true. And see that minimum is negative 2.8. Remember that if a value is between 0 and 1 when you log transform it, it's going to be negative. And I could get a maximum. I could get a standard deviation with the SD command. Right, so that's in the same units as this variable, not as the original yield variable, but as this axis, so about how much does it tend to vary around the mean. And sometimes what you want instead is variance. Depending on what sort of statistical test you're doing. So this is in squared units of the original, right? And if you recall from your statistics courses, the standard deviation is the square root of the variance. So what if you want to do statistics on pairs of variables? For example, I had another variable which was culm length that was also fairly normally distributed. Sorry, I abbreviated it CML here. And so if I just double check that with a histogram, right, I can see that one's also fairly normally distributed, like my transformed yield. So say I want to get Pearson's correlation coefficient with that. I can get that with the core function, COR. And in fact, I will bring up the help page for that, which actually lists several functions that we might be interested in right here. So if I want correlation between culm length, I'll put that in for the x argument, and then I'll put yield, the log transformed yield, in for the y argument. And again, by default, if I do this, it gives me NA because there was some missing data in there. So instead of NA.rm, here we have this use argument. And so I'm going to change this to pairwise complete obs here. Or I think complete obs will also work. So put a line break here just for space and readability. So use, and you need the quotes, complete.obs. The difference here is I think you can have x contain more than one variable, and if you want, it can give a bunch of different correlation coefficients. So it's a matter of whether you, for everything, you only want to look at the rows that have complete data, or just pairwise you want to look at pairs of values that have no missing data. So if I do that, I get the correlation coefficient. Now, as I mentioned, by default, that's Pearson's, and that's pretty good if you have normally distributed data. There's also the Kendall and Spearman coefficients, which have to do just with how the data are ordered. Like if you sorted it from smallest to largest value, do those tend to be in the same order between the two? So for example, let's see, so if I tried this with my untransformed yield here, I'm going to get a totally different value using Pearson's correlation, right? Because just how it's calculated is going to be very affected by that transformation. But if I take those two again and say change it to the Spearman coefficient, let's see, method equals Spearman, and I'll put that in for both. It's copying and pasting. So for those it's the same because whether it's transformed or not, it's in the same order. And Kendall is something similar, and you can look these up on Wikipedia if you want to understand how they're different. And as a reminder, if you take Pearson's correlation coefficient and square it, you get the R squared value. So if I take this whole thing and I'm going to square it using that caret, this would be r squared right here. Right, so the squared value would range from 0 to 1 versus the non-squared Pearson's correlation coefficient will range from -1 to 1. Right, you'll notice we have some others here. So we have covariance. So that might be useful if you need covariance for a particular formula, like I know in quantitative genetics, we would need it for doing things like genetic correlations. So right now this is no longer scaled from -1 to 1. This is scaled based on the units of these two variables. So now I'd like you to pause the video for a few minutes and determine which of the other variables in this data frame should probably be log transformed. And after you've transformed everything or not transformed certain things, figure out which variable has the highest correlation with yield. Okay, I'm going to show the answers, so pause if you haven't done it yet. So I log transformed yield, C-circ, B-circ, total combs, repro combs, and the comb dry weight. And I found that the total combs had the highest correlation with yield, and that was about 0.83. And now you're thinking, well, that's great, but how can I tell that that value, that correlation value, is statistically different from 0? So we're going to start getting into some statistical tests here rather than just estimating statistics. So first I'm going to look at core test, cor.tst. Right, and so it has a lot of the same arguments as core does. I don't see anything for ignoring data or not, so I assume that it's okay with some missing data. So let's put in our comb length and yield again. And then we'll start with the defaults. So if I run that, I get my correlation coefficient, which you might notice is the same one that I got when I estimated it this way. But now I have some other information, and what you're probably most interested in is the p-value. So this is the probability that if the true correlation was 0, this is the probability of seeing data that was that correlated. And we also have a confidence interval here. So we can say we're 95% certain that the real value is somewhere in between these two. Right, and that was a two-sided test. But say I only want to test that it's greater than 0 and not less than 0, then I would set a different alternative hypothesis. And if I run that, I get the same estimate of correlation, but a much lower p-value. Well, okay, in this case it's the same p-value, and I think that's because we have kind of reached the limits of what R can calculate. But let's say we're looking at a much smaller data set where we are going to get a slightly more meaningful p-value. So I'm going to put some brackets here to look at the first 100 items in each. So there's this colon between the 1 and 100, so that's going to grab the first 100 of each. So here I have a p-value of 4 times 10 to the -6th. That they would be this different or this correlated if truly they had a correlation of 0, versus if I have a two-sided hypothesis right, then I get a different p-value, and that p-value is it should be exactly double. And you'll notice if you take a look at some of these other arguments, again, I have options to use Kendall's or Spearman's coefficient if I prefer that. And I have an option to change the the confidence level for the confidence interval. So if I wanted 99% or something else like that, I could change that. And a few other arguments, which you can read about what they mean if you go down in the arguments section. Another test you might want to do is a t-test to see if two collections of observations have different means from each other. So if I look it up, I get a help page for that. So we have students t-test. You probably learned about that in statistics. So we can take a look at that. So again, we have an x and y argument. And testing if comb length and yield have different means from each other wouldn't make sense, right? They're measured in different units. They're completely different things. So that's not something that we want to test. But we might want to test if the yield was different between two of our field trial locations. So what I'm going to do, I'm going to take my log transformed yield, again, because this is a sort of test where we do want normality. And I'm going to subset it again with square brackets. And if you recall, we had a variable called LOC. I'm going to click over here so we can get a quick look. So I'm going to say MSI underscore data $LOC to get that column. And then two equal signs to test if something is equal. NEF. Now we're going to have a whole different video on subsetting, so I'm not going to explain too much about this, but hopefully this is useful and you can extrapolate for what you might want to do. So I had another location that was called HU. So say if I run this, what I get is a collection of values that were yield values, but only for the same rows where this LOC was equal to NEF. All right, so if I look, okay, well, yeah, I guess I'm I'm missing too many to count it up, but there are a bunch there, and then I could do that for HU, and I also have a big collection of values, slightly different number. So then I can run that. And then it does a t-test. And again, we have our alternative hypothesis, just saying that the null hypothesis is that these both have the same mean. And the alternative is that they have different means, but it doesn't indicate which direction they're different. So if you wanted to test that one was more or less than the other, you would use less or greater there. I have a p-value for seeing how different they are, and then I have my estimates. So I had a value of about 5 for NEF, which was my x, and then a 5.8 for HU, which was my y variable. So there are all sorts of other tests that I can do in R, like if I had count data and I wanted to do a chi-squared test, right, we have that available. Pretty much anything you want. If it's not actually in R's stats package, it's probably in someone else's package that you can get. So this is another case where Google is your friend. R is fantastic for statistics, and if you have a test that you've learned about in class and you want to do it, I'm sure it exists. So since we're getting on to about 20 minutes worth of video now, I'm going to save linear modeling, including ANOVA, for another video. But for exercises for this video, what I would recommend is go through some of the other columns in this data set. Look at the mean and standard deviation. Get correlations between pairs of variables, and spend some time looking at the distributions of those variables and thinking about what the most appropriate statistics are. And perhaps practice doing some correlation tests and student t-tests with other variables.